The general form of a d-dimensional linear program is as follows. So d here is a number of variables, and this is called a d-dimensional linear program. So we have variables x1 up to xd that are unknowns. These are the ones that we want to find. Then the input is given by these variables a's, b's, and c's. So all the a's, all the b's, and all the c's are given as part of the input. The variable c's, they define a linear function in this form. And ai's and bi's, they define a number of constraints. So a number of inequalities. In particular, we want to find the value for x1 up to xd that minimizes this function while satisfying all of these constraints. Okay. In our problem for finding the bridge, we have a two-dimensional linear program. And note that the roles of x's and b's are kind of swapped. In our formulation, a and b were the unknown, and xi and yi were part of the input. So it's just a minor change of variable, but it might be enough to confuse you. So in our problem, a and b's were the unknown, whereas here x's are the unknowns. You probably have heard about linear program, and you've probably seen some algorithms to solve it. If you have heard about this, then you have probably heard about the simplex algorithm. So in the general case, d could be part of the input, but we're studying a case in which d is a constant. For instance, in the bridge finding problem, d is equal to 2 because we have only two unknowns, so it's only a two-dimensional linear program. And as I said, these are the names. So that's called objective function constraints, and d is the dimension. The main result that we're going to cover in this week is the theorem that says such a d-dimensional linear program for a constant d can be solved in expected linear time. The constant that is behind this O of n is quite big, so it could be as big as d to the d. So it gets very inefficient as the dimension increases. That's not the best constant. So the best constant is technically something like 2 to the square root d or something like this, divided by times some small factor. So in general, even though this constant is much smaller than this constant, it's still not polynomial time based on the dimension d, and that's one of the biggest open problems in computational geometry. Note that we're going to solve this in the real RAM model, where we assume that all the inputs are real numbers. So for example, they could be floating points. If the inputs are integers, then it's known as integer linear program, and that's probably what you've heard about that can be solved in polynomial time. In our case, such a linear program, it's not known to be solvable in polynomial time because we assume the inputs are real numbers. So there is a specific modeling issue that makes this problem very difficult.